I want to thank everyone for joining us on this webinar. The objective of this webinar series has always been to get the information out to the industry, especially as travel is still limited, more so than others. Also want to thank the speakers today, Carl, Jeff, Sean, and Abigail, for taking time out of their busy schedule to present on these topics. And I want to go through an introduction of each speaker and their company at this time. Mr. Charpentier has been working electrical leak location surveys since 2001. With his background in electronics, he first started by making new equipment, has been improving methods in electronics since. He is part of the ASTM committee and has been publishing plenty of documentation pertaining to electrical leak location. Group Alphard's expertise includes performing leak location surveys on a variety of covered and exposed geomembranes, as well as developing new leak location technologies. Alphard also provides construction quality assurance, field supervision, and engineering for any waterproofing project. Our second speaker, Jeffrey Blum with Weaver Consultants Group, serves as a senior project manager in the solid waste practice group for Weaver Consultants. He has over 30 years of CQA experience in soil and geosynthetic line containment facilities throughout the U.S. His experience includes performing leak location liner integrity surveys since 2004. He participates as co-instructor at TRI Environmental during educational seminars and training for practitioners of leak location liner integrative surveys and provides trainings and educational seminars related to CQA. His other contributions to the field of CQA have included participation within ASTM and on committees which developed the Geosynthetic Certification Institute Inspector Certification Program, its predecessor, the NICET Geosynthetic Inspector Certification Program, and the International Association of Geosynthetic Installers Certification Welding Technician Program. Weaver Consultants Group is a privately owned civil, geotechnical, and environmental engineering consulting firm that was founded in 1990. It provides comprehensive solid waste services that include siting, design, permitting, construction management, and monitoring of landfill facilities. Weavers was founded on a strong belief that consulting firms should be dedicated to providing high-quality services for a select number of clients and projects. Our third speaker, Sean Callahan with HGI, is a geoscientist and the development manager at Hydro Geophysics Incorporated, with more than 15 years of experience in geophysical and electrical leak location technologies. His expertise encompasses leak location projects at the Hanford nuclear site, in the mining industry, and many other industrial complexes worldwide, and contributes to many presentations and published papers on geophysics and leak location technologies, and has published numerous technical papers on the topics. HGI is a solution-oriented geophysical consulting company and service provider to the environmental engineering, groundwater mining, oil and gas, and natural resource exploration industries. They specialize in the application of 3D geophysical methods and time-lapse subsurface monitoring of fluid flow through geological materials, leak detection, and liner leak location. And our fourth and concluding speaker, Abigail Gilson at TRI. She spent the first part of her career as containment facility design engineer and joined TRI in 2012 to focus solely on the implementation and innovation of electrical leak location technologies. She has over 16 years and 170 million square feet of electrical leak location experience, as well as contribution with numerous published papers, seminars, presentations worldwide, and leading ASTM task groups on matter at hand. TRI is a world-renowned independent testing lab, unaffiliated with any manufacturer or engineering firm. It provides testing, certifications, research, equipment development, and consulting on plastic materials in civil, environmental, and geotechnical applications.
Okay, so here's 4 handpicked projects from my list of leak location projects to be shown today. The first one is a project showing a lot of damages. Sometimes people really rely a lot on leak location to compensate for other mistakes or problem that occurred on site. This one was about a landfill expansion, and it was damaged beyond repair, in my opinion. So about the project, it was really near the bedrock, so not a lot of thickness in between. So they wanted to go and dynamite the whole thing so it could be flattened, but it was A lot of effort, a lot of money, and that option has been rejected. So then they wanted to fill the voids with sand to make it less edgy, but that required a lot of sand and was also aborted. So they went in for a third option, and it was to use a very soft LLDPE geomembrane and lay it down on the surface and follow all the angles. And this way it could be made impervious with a geomembrane. But the problem is that since the subgrade was really uneven, it was really complicated for the general contractor to put an even 30 centimeter or 1 foot thick layer of gravel. Meaning as soon as the top geotextile was covered with gravel, they didn't know the thickness. Even with a surveyor and a GPS, it was not possible. And another little factor there is that the old landfill has been in operation for more than 20 years, and they had no geomembrane at all. And it was okay because of the legislation at that time. But the new one on the left needed to have geomembrane on the bottom and needed to have a liquefaction also to make sure that there was no leak. So on the edge of the existing landfill, they didn't care at all that there was no liner, but right there, any hole was a problem. So it was hard to get the cooperation of everyone on site because of that point. So what happened there is that the gravel layer was spread on about 32,000 square meter or about 8 acres. We knew it would be complicated to do the job, so we went with a 1 by 1 meter dipole and grid, and we expected to do the job in 10 days. About a third of the surface was done after 12 days, and almost 200 leaks were exposed. And we had a meeting to change the strategy because it was a never-ending project. You can see the chart there that shows that 5% of the leaks were small, but 36% of the leaks were more than 10 centimeter wide. So a lot of big damage. Here's a map with all the spots that we dig on the site. We decided to go ahead and do a second pass with a bigger dipole, 2 meter by 2 meter, so we could maybe excavate all the big signals and leak spots, and then do a third survey and find the smaller one. So we had another 10 days of work and an additional 100 leaks. And then between the second and the third pass, the owner said that they wanted us to deliver a report saying that it was leak free, but we knew it wasn't. So the owner requested that we do the third pass, and that was another 10 days of surveying, 60 more leaks, and then it was still not leak free. So they said, well, it's going to be good enough for us. And we were called back like 2 months later just to double check the lowest point, where the head pressure is more important. And we found an additional 39 leaks in there, and that was the end of our part of the project. Okay, so the second project. We were requested to do a spark test proposal for a landfill in Canada. And the whole project was about 78,500 square meter, so that's about 20 acres. It was built with conductive HDP geomembrane. And the problem was that the installation and the survey was to be started in November and carry on for maybe 2 months. But we knew from experience that it was a really rainy season and that it would be challenging to do spark testing in there. So a little word about the spark test method. It should be done on a dry surface to avoid electrocution hazard and false positive. So if you have a network of puddle everywhere, it can spark a lot and slow us down. And the issue with the site is that maybe it rains 1 day out of 4, I don't know, but then the next day is almost completely lost because there's puddle everywhere. So you need to get your squeegee and remove the puddle as much as you can, pump them out, and then you're allowed to survey in proper conditions. So we propose to do a water puddle method, uh, and this method is a lot more tolerant to water, right? Water puddle. It's about the same principle. It works on bare or exposed geomembrane. Unless the main difference is that you push electricity in the puddle, and that's when you know there's a leak somewhere. If you have a lot of puddles on the floor, it can be complicated to locate exactly where the leak is. But that was, to us, the best approach, and the client approved this change. Uh, the result was that it lasted for 2.5 months, and we had 45 days of water puddle that were sometimes sunny, sometimes a little bit of rain, fog, but we had 27 days of full rain that were completely lost. A total of 66 leaks were found on the job and all repaired and tested until the job was completed. So on the pictures you can see, well, just a knife cut. That is pretty standard leak that we find with the water puddle method, but it's right next to an extrusion bead, which is not ideal because it's always tested with the vacuum box. So you should have spotted that one. We can see that they had a setup with a tent to try to get the job moving a little bit because it was way too much loss of time. And here on the picture you can see a little battery pack to power the water puddle system. And it's interesting because it's grounded to the subgrade, as it's always the case, and it's also grounded on the conductive part of the geomembrane, right under that panel. And since there was a big patch there, we cut open a patch and also grounded ourselves under that patch, so we can be sure that if there's a leak somewhere on the panel or the patch, we will be able to find it. So that's pretty much how it worked on that side. Okay, so the third project. That one is a little bit smaller than the other two. It was 11,500 square meters, or maybe 3 acres. The design was pretty interesting because it was double line, and we had a bituminous geomembrane on top and HDP liner on bottom. So it was the first time I saw that, 2 different products on the same pond. Here on the picture you can see that the first geomembrane was installed, then a layer of gravel that we had to survey with the dipole method, and at the end of the survey we could see a little bit of the BGM that was installed for the primary. The dipole survey happened on both layers with ideal condition, including the isolation that you can see here, that we requested that trench. The key trench was not to be filled until we're done with the work. So we have that exposed stripe of air or exposed membrane all around. The results were pretty fast forward. We just found one leak and it was right under the pipe. So ideal condition again, found one signal on the fine gravel, and we excavated it and we found that pipe, and we had that little extrusion bead that was leaking there. So they had it repaired, I think 8 times, because once you have water pouring inside an extrusion, it's really hard to dry it and to repair it properly. We had to cut open the liner on the top to get a shop vac down there to make sure that it was not leaking while he was doing the repair, but we managed it. What's interesting is that they called back a few months later saying, oh hey, the pond leaks right now. So we had to go there, and well, they wanted us to go there, and I said, well, it doesn't work when the ground is frozen. That's the theory. And the soil is not conductive, so there won't be any signals to be found. But they say, well, come and we'll just eat the pond. So I heard that a lot. Like people say, well, it's gonna be easy. We're just gonna tarp it and it's gonna be good. So I flew there, and the surprise was that there was a foot thick ice all along the floor. So that was even more complicated to get rid of. So I just had to sit down and enjoy the show of the general contractor trying to find a way to eat that. So he said, I'm gonna tarp it with big tarp and eaters. So they bought 4 by 8 foot plastic tarp with zip tie and tried to tarp the whole thing. So it was pretty interesting and funny to watch. They rented a 30 mobile blower, and those blowers just really burn gas and produce heat in some kind of big pipes, but they need electricity to work. So they had 10 tower lights to power the 30 blowers. So that's a lot of expenses right there. But it didn't do much. So uh, they said, well, what we're going to do instead is we're going to rent some heating hoses with mobile stations. So they rented 8 kilometers of hoses with 4 glycol station, and with those you can see all the tower lights on the side. So they said we're gonna melt the ice with that and eat the ground. But really, what they did is to cut the ice in and slide like that, because the warm cable were just melting their way through the ice until it reached the bottom, the floor. So it didn't work really well to eat up all the gravel. So finally, they decided to rent a really big unit, a eating truck. It really gets a 3 inches wide hose of freezing water and instantly push boiling water in another hose. So they took all the water in the pond and heated it up so it was warm enough to melt the ice and make sure that the gravel was warm in there. So to me, it was the world's biggest hot tub. It was really impressive to see. But then, okay, the ice was gone, but I still had to do a survey in there. So how can we make sure that the gravel doesn't freeze over as soon as they remove the hot water? And the answers was to keep the big truck and just blow hot water everywhere to make sure that it stays warm. It was a first for me and for the equipment, not really equipment friendly to survey in the steam like that. Uh, then we had some problem with the electrical isolation because the top of the slope was still frozen, solid, and we couldn't ask for any isolation, but it was time to check the theory that the gravel is not conductive when it's frozen, and indeed the whole thing was really warm, but there was no current going out of the site in the slope at all. So we had natural isolation all around with the ice. And then they did a survey and found one leak signal, but it really pointed toward a pipe penetration with all the big concrete slabs. And the owner didn't want to break the concrete to go see the state of the geomembrane under there. So that's where the project unfortunately stopped for me. Okay, and this one is a pretty small project, so just 2 slides. It was just really interesting because it was a fairly small pond, and it was an emergency water pond built straight on a parking lot. And they wanted to do leak location to make sure that it was leak free and they could access the water anytime they needed. So I sent a work proposal saying, okay, we'll need some water supply and we'll bring the hoses. But the contractor didn't read it all and he saw water, so he just filled the pond. And when we arrived on site, it was already filled. So not much we can do there. Like I said before, if there's puddle everywhere, it's hard to pinpoint where the leak is. So since I was there, I just put my equipment in the water and it was beeping, so I knew that there were leaking there. Just impossible to say where. So they emptied the pond, and then we did a survey on that tiny pond. We found 21 leaks, so that's pretty much, that's a lot for the size of the project. And the surprising thing about that is that 8 of the 21 leaks were caused by stone that were under the geomembrane and punctured through the thin geotextile and geomembrane because of the water's head pressure. So that means that on a normal survey, the pond would have been empty and I would have found the 13 leaks that was left by the installer. So knife cuts and scratches and pinholes. But I would have never found the 8 leaks caused by rocks under it. Meaning that it makes you wonder when you do a construction and you do all the job and all the testing, and as soon as the construction, the operation starts, you have no idea what's happening there, and it can be really fast to damage the geomembrane. So gotta make sure that everything has been thought thoroughly, so nothing is gonna damage the geomembrane after it's on use. That's it for me.
This presentation is a case study that deals with a project that had an excessive amount of large holes that reduced sensitivity excessively. This was a new wastewater treatment facility constructed in 2018 and 2019 in Michigan, and this facility consisted of 5 new ponds totaling 35 acres in combined area. The pond cross-section, constructed from the bottom up, included a sand subbase, a geosynthetic clay liner, followed by a 40 mil PVC geomembrane, covered with 12 inches of protective cover soil, which happened to be a sand. The geotextile and rock armor was then later placed on the side slopes after the leak location survey was performed. The specifications for this project required that the leak location be performed on top of the protective cover soil in accordance with ASTM D7007. For additional background, this is an overview of the 5 ponds, and we had pond 1 and 2, which were each 1 acre in size, pond 3, which was 15 acres, pond 4, which was 14 acres, and pond 5, which was 4 acres. Pond 1 and 2, which were similar in size, 1 acre each, consisted of several pipe penetrations, a sand protective cover soil, and during the survey they had provided an isolation around both lagoons at the edge of the anchor trench. Ponds 1 and 2 survey was completed October of 2018 and were found to have a total of 8 locations with small holes. These holes included rock punctures, knife cuts, and some equipment damage. Now you'll see in these lagoons that we have a couple areas with focused damage, and this is where the ramp came in to bring the material into the pond. Same goes for pond 2 over here. We had excellent isolation on this project, and we were able to find the holes with very little issue, as can be seen by the voltage mapping. In pond 2 though, we had a few issues right here because we had multiple holes in one location that it made it a little bit difficult to pinpoint those holes. So during the survey of pond 2, where we had multiple holes, we were able to locate this larger hole first, and then after that was isolated, we were then able to find these 3 holes all in one location, followed by the next hole several feet away from these holes. So these all acted together as one large signal, and it took isolating each individual hole or location to find them all. Pond 3, the 15-acre pond, was surveyed November of 2018, and the conditions were very wet during the survey. The isolation was not all that adequate due to the wet conditions, but we were still able to find considerable amount of holes because the wet conditions really did help the sensitivity of this particular lagoon. So as you can see here in the voltage map of Pond 3, we found 5 locations that included small holes or punctures and equipment damage. You can see that along this edge we had sensitivity issues with edge contact, and same goes for these areas along this edge. But we were able to find the locations. Even though the artificial leak rate here was still a little difficult to see, we still had no issues finding the holes in this lagoon, particularly this larger hole right here. Pond 5 survey was completed in April 2019, and this was the 4-acre pond that was kind of a triangular in shape, and the conditions in this lagoon or pond were excellent. We had really good isolation, and we were able to see our artificial leak with really no issues on the voltage map, and we were able to find 2 locations that had holes that was very easy to see in the voltage map as well. Pond 4, and the last pond to be surveyed, was the project that became the most difficult for us. This was the 14-acre pond that at the time of the survey, which was April-May of 2019, conditions were very wet. Isolation was okay, but we still had a few issues with edge contact. As you can see on Pond 4, here's a photo of the edge contact that we had where water draining from the sand outside the lagoon or pond was wicking into the inside of the pond, which was creating edge contact. And we had this in several locations around the pond. So at the beginning of the survey of Pond 4, when we set up to perform our sensitivity test and locate the artificial leak, we had very little success. The sensitivity on this pond was just very poor, if almost non-existent. We couldn't identify the artificial leak upon our initial surveying. So as a test, during troubleshooting, we took our instrument and spanned across the isolation zone, touching the sand or 1 foot of the leak location equipment on the sand inside the lagoon with the soil outside the lagoon, and we had very little voltage, meaning that our voltage was leaving this pond through something very quickly and giving us very poor sensitivity. So we started our survey in April, and it actually took us 2 days to get the troubleshooting complete and get across this lagoon almost 1.5 times. And during the survey, what we found is 14 locations that included very large holes that was really giving us the problem. So here's one of the locations we found. This was a 20 by 20 area, I believe, that the liner had just tore, and this was a result of the contractor being in a rush to get this project done in the coldest time of the year, pushing sand and probably very heavy loads of sand that was stretching the PVC to the point that it was just snapping and tearing. Here we have another hole. This I believe was 20 by 50, and again it was just from stretching the liner tight during placement of the sand causing the liner to snap. these large holes was making it very difficult for us to locate anything smaller than these. We were able to find some, but these were creating quite a voltage draw. And believe it or not, the size of these holes made them even more difficult to find than what would a typical hole be, because of the way the voltage was behaving at these locations. So here's the second survey of Pond 4. So after we located those 14 locations and isolated them and repaired them, we came back, and over the course of 2 more days, we surveyed this lagoon again, hoping to find all of the final holes that may exist in this lagoon. And as you can see, we found 27 additional more holes in Pond 4. Here you can see our artificial leak. It still is not easily seen in this voltage map, but it has a lot to do with the fact that it is surrounded by a lot of holes, particularly big ones over in this area. And we found additional more big holes. So here is one of the larger holes that we found during this second survey. And this is actually where the haul road, or one of the locations of the haul roads was that coming into this lagoon. And just in the amount of heavy loads that the dozers were pushing into this lagoon just stretched this PVC tight, causing it to snap. Here's a location at a second tear where the haul road came into the pond. And again, as they're pushing sand down slope, it just stretched the geomembrane and GCL tightly to the point where it just snapped. So this is an overview of Pond 4 during the second survey mobilization, and you can see that, you know, we're opening up or exposing a geomembrane in several locations so that we can isolate them and find additional holes. So the second survey, like I said, it resulted in finding 27 additional locations, and you can see the sizes of some of these locations. We have 18 by 20, 10 by 10. I believe down here we have a 40 by 40. But even with these large holes, the sensitivity is improving, so we're starting to find a lot of smaller holes throughout this process. So after we exposed all those and performed all the repairs, they covered everything up, and we came back and did a third survey spanning over 2 days that resulted in finding 15 additional locations. And what you see here is just where we had to move the injector around. So these weird lines in the voltage map is just injector moves. But what you can see is the artificial leak is starting to show up a little bit better right here. So our sensitivity has improved considerably since the first survey. And we were able to find these additional 15 locations with very little issue. So here we show the additional 15 locations, and there are a couple big ones, 25 by 50, 10 by 10, but we're able to find all of these smaller holes. And I call this the third survey, but we actually performed, in essence, a fourth survey, just making sure that there was no holes left behind after this. So here's a photo of one of the holes that we found during the last survey, and again, it was just the PVC being pulled so tight that it just snapped in a weird formation. So in summary, you know, the large amount of holes that we found during this lagoon was largely because the contractor, the general contractor, was extremely behind schedule by almost half a year. So to get pond done or completed as quick as possible while they're completing other ponds, they subcontracted to someone else to place the sand. And this contractor just was inexperienced in how to properly place sand over a geomembrane. And also, the placement was performed through the winter months, meaning the PVC was extremely cold and brittle from the low temperatures. So it did not have much elongation due to the cold temperatures. And there just appeared to be a poor third-party oversight, whether they were not present or they just not paying attention or not knowing what they were doing during placement to prevent much of this damage. Thank you for your time.
Thank you, Jeff and Carl, for presenting those case studies. And thank you, everybody, for coming and attending this final episode on electric leak location technologies. What we would like to do is take a different approach than presenting case studies and present a number of different scenarios that we here at HGI have encountered over the years. Many of these different scenarios are based on preparation, which is really the key to getting on site and hitting the ground running when performing leak location surveys. So one of the big important aspects of getting these things started is communication, right? It's paramount and it's essential to consider as both the client and the ELL provider often know little about each other. Additionally, the client may not even have a complete knowledge of their own structure, facility, or site. So it's really important to consider, are you asking the right questions? If you are a purveyor of leak location, or if you're a client that has a facility that needs leak location, do you even know what the right questions are to ask? And that's pretty much our job to help you through this process. And it's our job to make sure that we're getting as much knowledge as we can about your facility so that when we get on site, we can hit the ground running. You know, understanding is a two-way street, and comprehension is the key to the success of making these surveys work and be successful. So another area of scenarios that we're going to talk about is how many companies are involved, teams, groups, or people, and that you're going to be working with. In a lot of cases, it's not just client and provider. There may be a number of different groups that are working towards solving this problem. And then finally, what are the tasks that the client is responsible for, and what are the tasks that the LLL provider is responsible for? So both parties are going to have different tasks, and it is essential that each understands what it is they need to do to make sure that when your provider shows up on site, things can go smoothly and successfully. There's a lot of information that needs to be transferred from the leak location provider to the client and from the client to the provider in order to get things moving successfully. So one of the most important parts of the process is the questioning process, which is where the prospective client learns about how leak location is done, and the surveying company learns about the facility and the structure where the leak location survey is going to take place. So here's our first case in point, navigating slopes. So we were doing spark testing. We were spark testing the primary geomembrane for a double-lined pond. The liner was smooth, conductive-backed, HDPE. It was fairly old, and the slopes were about 3-to-1. The liner was being cleaned by another contractor, and in fact, they were still there working on the facility when we arrived. Now, the client stated to us that the contractor had no problems navigating the clean, dry slopes. However, when we arrived, the reality was much different. The contractor was still there. They were working on other projects associated with this facility. And what we realized right away was that they weren't navigating the slopes at all. They actually had developed defined pathways from the top of the slopes down into the pond so that they could get into the pond to do their work. And funny enough, they would occasionally go up the side slopes, but they would need to do a running start, run as fast as they could to get the momentum to work their way up the slopes. It was almost a casual game that they played every once in a while to see who could do it and who couldn't. So obviously this wasn't going to work for us. However, the solution was really simple. All we needed to do was get a harness and rope and have somebody pull me up and lower me down. The challenge here is that whenever you show up to a site and you have to accommodate some type of challenge that you didn't know about, you were unaware of, there's a cost. And in this case, the cost was time and money, of course. Because what needed to happen was we had to acquire the equipment, we had to set it up, and then we had to find a couple of people to pull me up and lower me down. We needed two because after a while, one person would get tired and they would have to trade off with the other person. And this also made data collection longer, right? Because originally going into the project, we felt that we could, if the slopes were navigable, we could walk up and down the slopes with no problem. But being that we needed to be pulled up the slopes and lowered down, this now increased the time it took to do the survey. And on top of that, anytime you go to, major facilities like this, there's always safety concerns involved. So now we had to modify the safety plan so that we could do our work safely. In every case, this made the survey longer. And it's frustrating for the client because now their facility is out of production longer and the survey is going to cost a little bit more. And it's frustrating for the leak location provider because they're going to be at this site longer than they expected, and they have to push other projects down the road until they're finished with this one. So the really important lesson to learn here is that the more information everyone has so that when the leak location provider shows up on site, they can get started quickly, and this will enable them to finish on time so that everyone's happy. Anytime there's changes with any projects, there's always going to be costs. Here's our next case in point. Mixing non-conductive and conductive liner materials when repairing a pond. So we had a situation where we were doing a spark test on an older pond. The pond had been drained and cleaned. And when we got to the pond and we started doing the test, we realized that some of the past repairs that had been made from previous surveys, some of the areas they used non-conductive liner material. And in fact, in other areas, conductive liner material that was used for repairs was put on backwards. They had flipped it over and the conductive part was on the top instead of the bottom. Now, for all these areas, we couldn't test, right? We couldn't test any of them to see if there were any leaks using our spark testing equipment because there was no conductive backing on the bottom side of the liner. And they had another situation at the same pond where a portion of the slope had been damaged by a storm. And the liner was too badly damaged to put back, so when they repaired it with non-conductive liner material. So a whole portion of the slope couldn't be tested. So what's the solution here? Well, in this particular case, spark testing wasn't going to work for the non-conductive portions of the liner. Now, because the repairs to the slope were new, they opted simply not to test it and instead go ahead and fill it up. And their thought was that if they filled it up and they found leaks, then what we would do is a full pond test, right? Because what we'd have to do is flood the interstitial layer, the space between the primary and secondary liner, and that would be used as our conductive media to carry current to find leaks in the non-conductive material. So we didn't do that. They filled it up and everything was fine, luckily. But so what are the costs here? Well, the costs are that certain areas of the pond couldn't be surveyed. And in order to survey them, there would be an additional method that would need to be used to find holes in those particular sections, and that would cost more time and more money. Our next case in point is barriers to work. So we have showed up to a number of water-covered pond surveys where we're surveying the primary geomembrane of double-line ponds, and we've encountered floating platforms, scaffoldings, and other in-pond structures that we weren't aware of. Now, in these particular cases, usually the solution is pretty simple. In fact, many of the solutions to isolating a pond or solving barriers to work are fairly simple. In these cases, the platforms or scaffoldings simply need to be removed. However, when you show up on site and they're not done, this takes time. It doesn't happen in a second. It could take hours or even days, which would, impede you from starting your project. In another situation, we encountered a pond where the water surface was covered with bird balls. And the bird balls were packed so tightly together that we simply couldn't move people or equipment freely through the water column in order to do the survey. The solution to the challenge of the tightly packed bird balls is to simply add more water to disperse the bird balls and allow our equipment to get into the water column so that we can do leak location. What are the costs? Well, we had to wait for the pond water level to be high enough so we could do our work. And for those of you in attendance today and watching this video in the future, you know that some of these sites are absolutely massive, acres and acres. And to add enough water to raise the water level just a few feet could take days. And all the while that this is happening, your leak location provider is sitting there being paid to wait for the pond to fill up to the level it needs to be so that the work can be done. In our next scenario, we talk about multiple contractors. In this particular situation, we were surveying a soil-covered liner for a new heap leach pad. The geomembrane was below about 2 to 3 feet of what's called ODF. And for this particular project, there were multiple teams that included the main client, the mine, an engineering company, the construction company, and the liner leak location company, AGI. As we are all aware, perimeter isolation is one of the major keys to doing leak location surveys effectively. Now, in this particular image for this project, we can see this beautiful ribbon of exposed geomembrane that wraps its way around our survey area. In this particular scenario, the major challenge was a loss of sensitivity for the soil-covered liner survey. We just couldn't keep any current in the area to help us find leaks. So what happened? Well, the leak location company was on a break to wait for progress on the leach pad construction. And during the hiatus, the engineering company and construction company told the mine, the primary client, that they could start stacking the leach pad. Now, this wouldn't have been a problem had the appropriate actions been taken. So the mine built a haul road over the exposed liner, which broke our isolation barrier. This image is a little fuzzy, but you can definitely make out the mine's new haul road that they are using to stack their new leach pad. Now on the left side of the screen, you can see a black line that bisects their new pad and the earth on the other side, and it runs right into their haul road. Now, in this particular situation, when we're trying to do leak location, there is simply no way to overcome this type of isolation barrier breach. The solution to our isolation challenge was, again, fairly simple, but the implementation of that solution is the complex part. What needed to be done? Well, the construction company needed to come in and dig a trench down through the haul road to the liner below, and then install a piece of liner that would come up from that lower level liner through their trench, bisecting the haul road, and thus restoring the perimeter isolation of the survey area so that we could continue. Now, what were the costs of this? Well, the mine had to stop putting ore on the pad. They were unhappy about that. The construction company had to go in and dig the trench and do the work, and that took time. And the leak location company had to wait for all of this to be done. Again, these things take time. It took almost a week for them to complete the process before we were able to get back out on site and finish this part of the survey. In this set of case in points, we're going to talk about tasks. Who does what? What does the client do? What does the leak location provider do? So we were doing a deep water survey, and we're working with the client to make sure that when we showed up, all the isolation procedures were done and in place. What happened was the client was unclear on their action items for isolating stainless steel pipes. And when the leak location crew arrived, we had to delay the survey because some of the metal pipes weren't isolated in the appropriate fashion. The steel piping that was going into and out of the pond caused an isolation breach and was bleeding off current from the survey area. What needed to happen was that an air gap needed to be created at a joint and that would improve electrical isolation. Again, simple fix, but it took some time. These pipes are big and heavy, and they needed a lot of workers to go out and create a few inches of gap so that the isolation could be restored. So for our final case in point, we're going to present a positive scenario where the leak location provider and the client work together to solve problems before the leak location provider ever showed up on site. And what happened is that we were doing spark testing on a black HD EP liner in the desert in the middle of summer. What happened? Well, the liner was simply too hot to survey during the day. Surface temperatures of the liner were more than 150 degrees. Now, you can only imagine that having people on the surface of these liners at those temperatures would be grueling, and it was. So what we decided to do was do the survey at night. Now, an added benefit of doing the survey at night is that the liner cooled and all the wrinkles that developed during the day because of the heat went out of it, so the liner was a lot flatter to survey, and this made the survey go much quicker. So what are the action items of the client? Well, they need to supply light stands to illuminate the liner surface so that we can see to do our work. They'll need to supply site personnel for night watch safety. Things are different at night than they are during the day. And they'll also need to design a safety program for the night survey. What are the provider's action items? Well, we're going to need to supply flashlights and headlamps and perform a safety review for the night work to make sure that we're all on the same level when it comes to safety at the site. Everything worked out great. We were actually able to get the survey done ahead of time, and the survey was a complete success. We found holes, they were repaired, and so on. So what's the lesson with all these different scenarios? The lesson is that communication matters. It's paramount that both parties, the client and the provider, communicate in such a way that we know of all the obstacles so that when the leak location provider steps on site, they can hit the ground running, get the survey completed on time, and everyone can move forward. Thank you very much. I appreciate all of your time. And now, on to Abigail.
My first case study illustrates how poor survey area isolation affects sensitivity. So this project was a double-line landfill. We're surveying the primary geomembrane. The allowable leakage rate at the site was 20 gallons per acre per day, and it was leaking excessively. Two sides of the landfill cell had sufficient isolation. These were the sides for future expansion. So the geomembrane, the primary geomembrane, was bare and visible on two sides. But the berm adjacent to the road and the tie-in to the existing landfill were not isolated. It was just complete continuity in the sand cover material. So for double-lined sites, we do have a reasonable chance of success if the leak detection layer is isolated from ground. So this particular project, that wasn't the case because the GCL was tied into existing, but it is very atypical to have a leak detection layer that's completely isolated from ground. And you certainly can't rely on it. Even holes in the secondary geomembrane can compromise isolation. So the artificial leak was detectable. It was placed away from those grounded edges. Sand as a cover material is not really conductive, so having that sand less conductive will help. So we decided to proceed with the survey because it was a really large landfill expansion and the tie-in area was very long. So it would have been a lot of work creating an isolation trench there. So we kind of crossed our fingers and did the survey anyway. One leak was detected during that initial survey, but it was located away from those two grounded edges. It was one small leak and it was repaired. However, after the repair, the landfill continued to leak excessively, so obviously that was not the problem. At the request of the engineer, we quadrupled the measurement density. Using a 10-foot dipole, we went from a 10 by 10 spacing to a 5 by 5 spacing. So what that does is it quadruples the time taken to survey and therefore quadruples the cost of the survey. So what we ended up with was just more resolution of a poor quality survey with no real increase in sensitivity. And the reason they recommended this is because D707, that ASTM, makes it sound like all you have to do is increase measurement density to increase sensitivity, which is not the case. You really have to improve the site isolation and conditions. During all of these surveys, we found many anomalies along the tie-in, but they just couldn't be pinpointed because there was so much excessive current going out of that tie-in area. So we finally recommended that the contractor had to isolate all of the edges of the survey area in order to locate the source of the leakage. So in the end, 8 leaks were found. They were all along the tie-in, including this leak here, which was very large. So this just goes to show how large of a leak can be undetected with poor survey isolation. My next case study shows how even existing leaks in the lining system that you're trying to find will compromise the sensitivity because the current will travel the path of least resistance. So this project was a single-lined wastewater pond, and it had about a foot of sand covering the geomembrane. We set everything up and the artificial leak was not detectable at all, even when we were directly on top of it with the dipole. And the apparent issue was ponding water against this installed concrete ramp. So here's the concrete ramp, and even though they created an isolation trench for us as best they could, there was ponding water here. So we went ahead and evacuated that water with the shop back, but there was water slowly weeping out from that cover material, so we couldn't keep it completely dry. So what we did is we installed one person at that ponding water with a shop vac that was continually vacating water from that isolation trench during the test. We just made sure that the dipole was working and the test appeared to be functional, and then went ahead and proceeded with the test. An additional challenge we had with this project is that the dried wastewater solids were very flaky and crusty on top. and we had no water truck, so we had to water by hand with a watering backpack. It was also difficult to move around. So anytime you have a non-homogeneous surface like this that's flaky and kind of dry, you're going to get some erratic data. Fortunately, our data was clean enough to see two really nice textbook leak signatures in the data, and we ended up finding two very significant leaks. You can see the geomembrane here, and some sandbags propping up the geomembrane. This is probably a 2-foot diameter tear here. So this case study really illustrates why you might want to proceed with the testing even if the artificial leak is not detectable. You do what you can with the survey area isolation, but at some point you just have to proceed with testing and hope that it works and locates the leaks. There was a chance that we wouldn't have found anything for this project, and maybe that concrete ramp would have affected the isolation, but you just don't know sometimes until you proceed with the test. My last case study shows how a project can quickly turn into a nightmare if the owner and site engineer don't understand the testing technology. So we requested sufficient moisture for the primary geomembrane of a double-line landfill to actually leak before the testing event. The site engineer performed a theoretical calculation to advise on how much water to add to the cover material. And this particular site was experiencing a severe drought, high temperatures, very arid conditions, so probably most of the water they applied to the cover material just evaporated. When we came to do the test, the cover material and the underlying layer were sufficiently conductive to perform testing. However, the water that was applied never got down to the top of the geomembrane, so no leaks were detected during the testing event. After the testing event, we had extreme back-to-back rain events. It was like historical rain events. And the primary geomembrane was shown to be leaking in excess of the site's allowable leakage rate. So this wouldn't have been a big issue if we were just asked to come back and retest, because we would have found those leaks at that point. But instead, the project just turned into a hornet's nest of lawyers, and everybody got sued. And at the end of the day, the only folks who made money were the lawyers. So this is not a path that you want to follow. In summary, we would just like to reiterate how critical it is to properly prepare for a survey, especially survey area isolation. In order to do this, communication is key. The earlier the better. Even before the project bids, the contractor needs to understand what is required in order to prepare properly for a test. If things go well, the test is cheap and fast. But if things don't go well, the testing can affect the project schedule and the budget. Multiple large and an excessive number of leaks, which is hard to anticipate, can reduce survey area sensitivity in the same way that poor isolation affects sensitivity. The site and construction materials leading up to and during the test should be constantly evaluated, especially in cold conditions that might result in freezing materials. ELL should not be treated as a fix-all for site issues. It's one tool that should be used at the end of construction to make sure that everything was done properly. And hopefully by now you can appreciate the significant expertise involved in troubleshooting problematic sites, identifying testing issues, and making sure that you're going to get the best test possible out of your project. With that, we would like to open it up for questions.